Now today I'm going to begin the lecture on groundwater. Now groundwater is the water contained in pore spaces or other openings within bedrock or regolith, and for the most part constitutes less than 1% of all water on Earth. And although groundwater is 40 times more voluminous than freshwater lakes and streams, it only holds a small fraction of Earth's fresh water, where most fresh water is stored in glaciers and polar ice. Groundwater mostly originates as rainfall, and from there the rainfall percolates through soil and rock down to the groundwater system. And once underground, groundwater slowly migrates towards nearby lakes, streams, the sea, or ocean. So groundwater originates as rain and melting snow, and the groundwater in turn is recharged by way of surface water that infiltrates into the ground. Infiltration capacity is controlled by such factors as the intensity and overall duration of the rainfall, prior wetted conditions of the soil, things like soil texture, the overall slope of the land, and even the nature of the vegetative cover. Here we see the share of total volume of fresh water on Earth. And as we looked at before, we saw that ice sheets and glaciers by far store most of the fresh water on Earth, about 85%. Groundwater constitutes about 14.6% of all the fresh water on Earth, and the rest of it goes into lakes, soil moisture, water vapor, and rivers. If we ignore the ice sheets and glaciers and only look at the liquid water, the unfrozen water on Earth, we see that groundwater contains most of that liquid water, about 94%, the rest being stored in lakes, soil moisture, atmosphere, and rivers. These diagrams show the sources of all fresh water in the United States. About 77% of the fresh water in the U.S. comes from surface water, and the rest, about 23%, out of the groundwater system. If we just look at the groundwater, about most of the groundwater is tied up in irrigation, about 68.4%, and another 19.3% goes into public supply, and the rest distributed upon such things as mining, aquaculture, livestock, industrial uses, individual wells, and thermoelectric power, mainly geysers and hot springs, things of that nature. So by definition, groundwater occurs within approximately 750 meters of the Earth's surface. And the Earth's surface, whether it's soil or sediment or even rock, can be subdivided into an upper zone called the unsaturated zone. Here, the pore spaces are filled with water plus air. But as we go deeper into the subsurface, eventually we encounter what's called the zone of saturation, where pore spaces are filled with 100% water. Now, by definition, the water table is the upper surface of the saturated zone. In other words, it can be considered as a two-dimensional plane that separates the underlying saturated from overlying unsaturated zone. Now, the groundwater table intersects the land surface in places like lakes, marshes, springs, and streams So, for example, this photograph, which shows a series of lakes, those lakes constitute the level where the groundwater intersects the surface. Now, the groundwater table somewhat imitates the overlying land surface. It tends to be higher in places like hills, whereas tends to occur lower in valleys and particularly within stream valleys. What's more, the groundwater table rises and falls with the seasons. It may drop during dry seasons and rise after, for example, heavy rainfalls. So here, for an example, is a cutaway view showing a normal water table. And again, this illustrates how the height of the water table somewhat imitates the overlying topography. Notice that where we have hills, this is where the water table tends to be higher, whereas in valleys, the water table is lower. And also notice that the water table intersects the land surface at the stream. And what's more, to the right, we have a well that penetrates into the zone of saturation. So at this point, the well is a producing well. It's able to extract water from the groundwater system. But then during times when droughts occur, or maybe during dry seasons of the year, the water table falls. This in turn reduces the stream flow. And notice now at the well to the right, the well does not reach the water table, so during dry seasons this well is non-productive. Also notice that the level of the stream has dropped in response to the overall drop in the water table. On the other hand, during wet seasons, the water table rises and stream flows increases. And during those times, notice again that the well on the right is producing water from the zone of saturation. Now, throughout the United States, there's a groundwater network, basically an array of wells where water levels are routinely measured. For example, the U.S. Geological Survey, in conjunction with state agencies, maintains an extensive network of about 20,000 observational wells throughout the United States. And map, for example, shows the distribution of the network wells in the state of Missouri. And if you look at the figure to the left, it shows a typical well. And above the well, there's a recording box. And if you look at the well itself, there's kind of a counterweight float that continuously measures the height of the water table at that particular well. And that data is then remotely transferred to a nearby recording station where the data is constantly being collected for that particular well and possibly wells within the particular area. If you look at the graph in the lower right-hand corner, the vertical scale is the depth to the water table. And we're looking at different times of the year, ranging from July 1st of 2006 over to March 1st of 2007 towards the right. And notice during the dry season, during dry weather, we see that the depth to the water well increases over several weeks to months. But then during periods of rainfall, we see that the depth to the water table rises. And this is due to the infiltration of the rainwater as it enters the groundwater system. Over towards the right, we see during the rainy season, the depth to the water, to the groundwater table is quite a bit shallower during the rainy seasons versus the dry seasons. So it doesn't really take long for the groundwater table to rise or fall in response to the overall moisture conditions that are occurring within that particular season or series of weeks. Now, groundwater percolates through soil, regolith, and rock through open pore spaces or fractures within the material. And water moves slowly through pores along mostly parallel thread-like paths, as shown in this figure to the right. Now, one measurement of groundwater is the term porosity, which refers to the percentage of open spaces within the given volume of regolith or rock. And porosity in most rocks is usually less than 20%, but can be as high as 50%. So basically, it's just the proportion of the rock or regolith volume that's comprised of simply pore spaces that can contain groundwater. So if you look at the upper left-hand block diagram of sand, notice that the sand in figure A has a lot of pore spaces in between. So this is a pretty good aquifer. It can be a good source of groundwater. To the right, though, in figure B, we see a sandstone where the pore spaces are mostly filled with mineral cements. And at that point, the porosity has been dramatically reduced. In the lower left-hand corner, figure C, we have a fractured granite that, and the fractures can constitute a certain amount of porosity within the rock. And in the figure in the lower right, figure D, we have a limestone that's crisscrossed with vugs and caverns and things of that nature, which impart quite a bit of porosity to that particular limestone bedrock. So those are just examples of different examples of porosity. Now here we see a porous sand which has high porosity. Notice that between the sandstones there's quite a bit of pore space which can hold groundwater. However, mineral cements can partially close the pore spaces, reducing the overall porosity. Fine-grained sandstone, in turn, tends to be less porous than coarse-grained sandstone because finer particles tend to exhibit smaller pore spaces between the individual grains. And what's more, poorly sorted sandstone with irregular shapes tend to be less porous than well-rounded sandstones with rounded grains, simply because the smaller grains can fit and partially close the pore spaces between larger grains. So it just depends on the overall characteristics of the soil or sediment or bedrock as to exactly what the porosity of that particular material is. Now, permeability, on the other hand, is the measure of how easily a rock allows fluids to flow through it. And in general, sandstones tend to typically be more permeable than clays. In the upper right-hand figure, for example, we see a sediment that has low permeability because although there are pore spaces that can contain water, those pore spaces are isolated from one another, and therefore there's really no connectivity within that particular sediment. On the other hand, in the lower figure shows a sediment showing high permeability because here the pore spaces are interconnected and water can flow through the material quite easily. On the other hand, unfractured shale tends to have very low permeability because the pore spaces are not interconnected. We see here in this particular example of unfractured shale that there are very small amounts of pore space between clays and silt grains. And what's more, there's no contact between the individual pores, so the water the pores tend to remain isolated from one another. But overall, there's a rough correlation between porosity and overall permeability. Gravel, for example, tends to have very high porosity and also very high permeability. Coarse to medium sand, high porosity, high permeability. But when we get it down into smaller particles like fine-grained sand and silt, notice that both the porosity and permeability decrease to values of moderate to low. Sandstone, in turn, that's moderately cemented, ranges from moderate to low porosity and low permeability. And shale, for the most part, whether it's fractured or unfractured, usually exhibits very low to very low porosity and also very low permeability. Any questions? Additional measurements include such things as specific yield. Specific yield refers to that portion of groundwater that will drain under the influence of gravity and therefore constitutes the water that is readily available for use. Whereas the specific retention refers to that portion of the groundwater that remains bound in the material, in which case the water is retained in the material and is unavailable for use. And here's some examples of porosity, specific yield, and specific retention. Notice in all of these cases that the porosity is simply the specific yield plus the specific retention. Clay, here's an example of a clay with a very high porosity, 50%. However, notice that the specific yield is 2 and the specific retention is 48. Would this clay be a good source of groundwater extraction? Could we extract groundwater from? No. This clay would make for a very poor aquifer because most of the water is retained within the material and cannot be extracted as a result. Here's a sand with only half the porosity of the clay, 25% porosity. But notice here the sand has a specific yield of 22 and a specific retention of 3. Would this sand be a good aquifer? Yeah, it would be a good, really good source of groundwater. Gravel, here's a gravel with 20% porosity. We can extract most of that water. It has a very high specific yield, 19. So again, a very good aquifer. As is also this limestone with 20% porosity. This limestone has a very high specific yield, so it would also make for a good aquifer. On the other hand, we see that sandstone, which is mostly cemented, tends to have a fairly low specific yield and specific retention. Granite and basalt is, for the most part, not very good as a source of groundwater. Now, recharge in groundwater occurs in areas where precipitation seeps downward into the zone of saturation. And in areas of abundant rainfall, the recharge area may encompass the entire landscape beyond the stream channels, whereas in arid regions, the recharge only occurs beneath what's called an influent stream. And groundwater from there, regardless of the area of recharge, from there the groundwater flows into what are called discharge areas. Now, groundwater percolates from areas where the water table is high towards areas where the water table is low in places such as surface streams and lakes. So if you look at this overall figure, notice that in this case, the recharge area is pretty much the entire landscape, but the groundwater flow tends to be from areas where the groundwater table is higher towards areas where the water table is lower, typically nearby streams and rivers. Now, the looping flow lines may be thought of as a compromise between the downward pull of gravity and also the tendency of groundwater to move towards areas of reduced pressure. Again, from areas of recharge towards areas of discharge. Here, for an example, is what's called a gaining stream. Here we see that the water table intersects the channel, and notice that the stream is receiving water from the groundwater system, and as a result the stream is acting as a site of discharge. Now, this is typical of areas with abundant rainfall where the recharge encompasses, for the most part, the entire landscape beyond the stream. Here's an example of what's called a losing stream, which is connected. In this particular case, the water table sits lower away from the stream channel, in which case the stream is losing water to the underlying groundwater system. The reason it's called a connected stream is because the zone of saturation is continuous below the stream. Here is a losing stream which is disconnected, and as in the previous example, again, the water table occurs below the stream channel, and the stream is losing water to the groundwater system. But in this case, there's an unsaturated zone occurring below the stream, and as a result, it's disconnected from the main water table. And this is the situation that's common in desert-type arid regions. Oftentimes, throughout many months of the year, the stream is completely dry. Now, the shallow groundwater system typically discharges directly into nearby lakes and streams, as we saw in previous slides. On the other hand, we can also have a deeper sub-regional groundwater system that travels further and may actually bypass lakes and streams until finally discharging in a major river, and those are represented by the red arrows. We can even have a deep regional groundwater system that travels the farthest and will remain underground the longest, even bypassing major rivers, until ultimately discharging into large water bodies like seaways or oceans. Those deep regional groundwater systems can remain underground for thousands and thousands of years in some cases. Now, hydrogeologists are able to actually map the water table, and this is an example of how this mapping can take place. For example, we start out with a map of different well locations, and those numbers next to each one of those wells is the elevation of the water table at that particular location. Now, from there, we draw water table contours showing different elevations of the water table throughout the area. Has everybody worked with contour maps topographic maps. So this is basically the same thing. You just look at the elevation of the water table at different locations and then just draw contours to represent the overall height of the water table throughout this particular area. In this case, however, the contours occur subsurface. This is not the land surface. This is the level of the water table below the surface. And once we draw these contour lines, we can then, in this case, notice that the water table occurs higher within the upper right-hand corner of the map and is lowest in the lower left-hand corner of the map, simply by looking at these contour values. And then once we've done that, we can then construct flow lines that intersect at right angles to the contours and point in the direction of lower water table elevations. And in this way, we actually map the groundwater flow direction within the subsurface. If you're taking lab, you'll probably do this as a lab exercise. Okay. Pretty straightforward. So in summary, the time water takes to move from the ground through the ground from recharge to discharge depends on several factors, like, for example, the permeability of the material, the overall travel distance, and the path of flow, and can range anywhere from days to even thousands of years, depending on the situation. But for the most part, groundwater movement is exceedingly slow. Typical rates of movement is a few centimeters per day at the most. And the overall energy for movement is largely provided by the force of gravity. Another measurement we can take is what's defined as the hydraulic gradient, which is essentially the overall slope of the water table, and is simply determined by dividing the elevation difference of the water table between 2 points by the length of flow between these 2 points. As, for example, in this figure, H1 to the left represents the height of the water table in well 1, and then H2 represents the height of the water table in well 2. And we simply take the difference in elevation, H1 minus H2, and divide it by the horizontal separation distance between these two wells. And we get a number which represents the overall slope of the water table. It's quite similar to the stream gradient that we looked at before, except that it occurs below the surface. And so, as we would expect, the greater the hydraulic gradient, the steeper the slope of the water table. And we can take that value and apply it to what's called Darcy's law, which equates to discharge, represented by Q, as the product of the hydraulic conductivity K, which is a function of the permeability, times the overall cross-sectional area of the aquifer, times the hydraulic gradient, simply H1 minus H2 divided by D. So if the permeability remains uniform, the groundwater discharge will increase as the slope of the water table, in other words, the hydraulic gradient increases. And that's basically what Darcy's law represents. You don't have to memorize this equation. Just kind of keep in mind that Darcy's law is directly proportional to the hydraulic gradient. It certainly depends on permeability and cross-sectional area too, but if you keep those two variables constant, and anyway. Any questions? Now, the movement of groundwater can be measured directly. One way is to inject a dye in one well and simply observe where the dye appears in other wells. And from there, we can determine the velocity and direction of overall groundwater flow. Another technique is carbon-14 dating, which can date groundwater at various wells. And for the most part, the carbon-14 age tells us how long the water was isolated from the atmosphere after entering the groundwater system. Recall that as long as water is in contact with the atmosphere, it's continually receiving carbon-14 from the atmosphere. But once the water becomes separated from the atmosphere, then that starts the carbon-14 clock within the water, much like it when we looked at before carbon-14 dating, if you remember that. Don't worry about it too much. This is just some bit of information you can astound your friends with, again, on a Saturday night. But here's an example, again, of determining the velocity and direction of groundwater flow. Here is a plot of several well locations, and the numbers next to each well is simply the height of the water table within each of these different wells. And basically, we can inject a dye into one well, and then note the wells where the dye appears, and also note the travel time it takes for the dyes to appear. And we get a pretty good indication, which at this point, the overall flow direction of the groundwater. It certainly is not towards the north. It's obviously towards the south in this particular case. This also freaks out people who extract water from their well and all of a sudden notice that the well changes color, and they panic and they sue you, and you have to pay them millions of dollars. No. Anyway. Now, spring is a natural flow of water that occurs when groundwater emerges at the ground surface. And most springs tend to issue from fractured lava, limestone, or gravel. And of course, a well supplies water when it penetrates the water table and enters the zone of saturation. Here, for an example, we have a scenario before heavy pumping, where we have two shallow wells on either side of a deeper well, and this well in the center is going to undergo heavy pumping in order to irrigate the field. And this is the situation after heavy pumping. Notice that the central well has pumped so much of the water so fast that it created what's called a cone of depression. And a cone of depression forms when the rate of water withdrawal exceeds the rate of local groundwater flow. And in this case, the center well has pumped so heavily that the two shallow wells on both sides are now dry, because those shallow wells no longer reach the zone of saturation. And the reason it's called a zone of depression is because the people owning the shallow wells are very depressed. Actually, that's not why it's called that. But anyway. Any questions? Now, eventually, once that center well stops pumping, over time, the groundwater flow will diminish and remove that zone of depression, and the groundwater table will then rise again, and eventually those shallow wells may produce after, weeks or months. Now, aquatards are impermeable layers like shale that hinder or prevent water movement, whereas an aquifers are permeable rock strata or sediment that transmit groundwater freely. And good examples of aquifers are gravel, sandstone, and porous limestone. Now, this is a pretty busy diagram, but let's start with the overall cutaway view of this block diagram, where it shows the main water table and the underlying zone of saturation as that blue color. Now, if we look at the well on the very left, the well is shallow and does not reach the water table, so at this point the well is unsuccessful because it does not and is therefore non-productive. On the other hand, next to it is a shallower well that is productive, and that's because it's pumping from what's known as a perched water table. Notice that beneath that shallow well there's an aquitard, basically a shale layer that prevents percolating water traveling down from the surface from actually reaching the main water table. Instead, that percolating groundwater only reaches as far down as the aquitard and creates a secondary aquifer, which sits directly above the aquitard. And if we follow that perched water table to where it intersects the land surface, here we have springs issuing forth. On the other hand, if we go deeper to the main water table, that water table intersects the land surface at that nearby stream and for the most part dictates the height of that stream. So this is a pretty good diagram to really understand groundwater and how it relates to producing versus non-producing wells, springs, things of that nature. Any questions? Oh boy, this is our favorite slide. Means end of lecture.